In mathematics, one method of defining a group is by a presentation. One specifies a set S of generators so that every element of the group can be written as a product of powers of some of these generators, and a set R of relations among those generators. We then say G has presentation informally. G has the above presentation if it is the freest group generated by S subject only to the relations R. Formally, the group G is said to have the above presentation if it is isomorphic to the quotient of a free group on S by the normal subgroup generated by the relations R. As a simple example, the cyclic group of order n has the presentation where 1 is the group identity. This may be written equivalently as since terms that don't include an equals sign are taken to be equal to the group identity. Such terms are called relators, distinguishing them from the relations that include an equals sign. Every group has a presentation, and in fact many different presentations. A presentation is often the most compact way of describing the structure of the group. A closely related but different concept is that of an absolute presentation of a group. Background. A free group on a set S is a group where each element can be uniquely described as a finite-length product of the form, where the C-her elements of S, adjacent C are distinct, and I are non-zero integers. In less formal terms, the group consists of words in the generators and their inverses, subject only to cancelling a generator with its inverse. If G is any group, and S is a generating subset of G, then every element of G is also of the above form, but in general, these products will not uniquely describe an element of G. For example, the dihedral group D8 of order 16 can be generated by a rotation R of order 8, and a flip F of order 2, and certainly any element of D8 is a product of R, S and F, S. However, we have, for example, RFR equals F, R7 equals R-1, etc. So such products are not unique in D8. Each such product equivalence can be expressed as an equality to the identity, such as RF equals 1, R8 equals 1, F2 equals 1. Informally, we can consider these products on the left-hand side as being elements of the free group F equals less than R, F greater than, and can consider the subgroup R of F which is generated by these strings, each of which would also be equivalent to 1 when considered as products in D8. If we then let n be the subgroup of F generated by all conjugates x-1 Rx of R, then it is straightforward to show that every element of n is a finite product x1-1 R1 by 1, xm-1 room xm of members of such conjugates. It follows that n is a normal subgroup of F, and that each element of n, when considered as a product in D8, will also evaluate to 1. Thus D8 is isomorphic to the quotient group F, n. We then say that D8 has presentation definition. Let S be a set and let Fs be the free group on S. Let R be a set of words on S, so R naturally gives a subset of Fs. To form a group with presentation less than S, R greater than. The idea is to take Fs quotient by the smallest normal subgroup such that each element of R gets identified with the identity. Note that R might not be a subgroup, let alone a normal subgroup of Fs, so we cannot take a quotient by R. The solution is to take the normal closure n of R in Fs. The group less than S, R greater than is then defined as the quotient group. The elements of S are called the generators of less than S, R greater than, and the elements of R are called the relators. A group G is said to have the presentation less than S, R greater than if G is isomorphic to less than S, R greater than. It is a common practice to write relators in the form x equals y where x and y are words on S. What this means is that y-1 xr. This has the intuitive meaning that the images of x and y are supposed to be equal in the quotient group. Thus e.g., Rn in the list of relators is equivalent with Rn equals 1. Another common shorthand is to write x, y for a commutator x, y, x minus 1, y minus 1. A presentation is said to be finitely generated if S is finite and finitely related if R is finite. If both are finite, it is said to be a finite presentation. A group is finitely generated if it has a presentation that is finitely generated. If S is indexed by a set I consisting of all the natural numbers n or a finite subset of them, then it is easy to set up a simple one-to-one coding Fsn from the free group on S to the natural numbers, such that we can find algorithms that, given F, calculate W, and vice versa. We can then call a subset U of Fs recursive if F is recursive. If S is indexed is above and are recursively enumerable, then the presentation is a recursive presentation and the corresponding group is recursively presented. This usage may seem odd, but it is possible to prove that if a group has a presentation with R recursively enumerable, then it has another one with R recursive. For a finite group G, the multiplication table provides a presentation. We take S to be the elements G of G and R to be all words of the form, where is an entry in the multiplication table. A presentation can then be thought of as a generalization of a multiplication table. Every finitely presented group is recursively presented, but there are recursively presented groups that cannot be finitely presented. However, a theorem of Graham-Higman states that a finitely generated group has a recursive presentation if and only if it can be embedded in a finitely presented group. From this we can deduce that there are only countably many finitely generated recursively presented groups. Bernhard Neumann has shown that there are uncountably many non-isomorphic two-generator groups. Therefore, there are finitely generated groups that cannot be recursively presented. Examples. History. One of the earliest presentations of a group by generators and relations was given by the Irish mathematician William Rowan Hamilton in 1856. In his Icosian calculus, a presentation of the icosahedral group. The first systematic study was given by Walther von Dijk, student of Felix Klein, in the early 1880s, laying the foundations for combinatorial group theory. Common examples. The following table lists some examples of presentations for commonly studied groups. Note that in each case there are many other presentations that are possible. The presentation listed is not necessarily the most efficient one possible. An example of a finitely generated group that is not finitely presented is the Reith product of the group of integers with itself. Some theorems. Theorem. Every group has a presentation. To see this, given a group G, consider the free group Fg on G. By the universal property of free groups, there exists a unique group homomorphism phi, Fg whose restriction to G is the identity map. Let K be the kernel of this homomorphism. Then K is normal in Fg, therefore is equal to its normal closure, so less than G, K greater than equals Fg, K. Since the identity map is surjective, phi is also surjective, so by the first isomorphism theorem, less than G, K greater than M equals G. Note that this presentation may be highly inefficient if both G and K are much larger than necessary. Corollary. Every finite group has a finite presentation. One may take the elements of the group for generators and the Cayley table for relations. Novikov-Boone theorem. The negative solution to the word problem for groups states that there is a finite presentation less than S, R greater than, for which there is no algorithm which, give on two words U, V, decides whether U and V describe the same element in the group. This was shown by Pyotr Novikov in 1955 and a different proof was obtained by William Boone in 1958. Constructions. Suppose G has presentation less than S, R greater than, and H has presentation less than T, Q greater than, with S and T being disjoint. Then the free product GH has presentation less than S, T, R, Q greater than N. The direct products G times H has presentation less than S, T, R, Q, S, T, greater than, where S, T, means that every element from S commutes with every element from T. Deficiency. The deficiency of a finite presentation less than S, R greater than is just S minus R, and the deficiency of the finitely presented group G, denoted def G, is the maximum of the deficiency over all presentations of G. The deficiency of the finite group is non-positive. The Shaw multiplicator of a group G can be generated by minus def G generators, and G is efficient if this number is required. Geometric group theory. A presentation of a group determines a geometry, in the sense of geometric group theory. One has the Cayley graph, which has a metric, called the word metric. These are also two resulting orders, the weak order and the Bruhat order, and corresponding Hasse diagrams. An important example is in the Coxeter groups. Further, some properties of this graph are intrinsic, meaning independent of choice generators.